So now that you know the definition of derivative, we're going to try to apply it and as well as use it to kind of verify the things we already know using the power rule. So for example, if we give you a function f of x equals x squared plus 4x 2, you can try to find the derivative f prime of x using 3 different methods. One, you can use the definition of the derivative. And we know that the derivative of a function is equal to the limit as the distance between two x values get closer and closer of the change in y over the change in x. So let's do it. Okay, so we know that f prime of x is equal to the limit as the distance between the two x values get closer and closer of the change in y minus the change in x, or over the change in x. So we know it's the limit as h approaches 0. So this x plus h right here is our new x value. So I just plugged it into our original function. Okay. So let's simplify it out. So we've got x plus h squared is x plus h times x plus h. Plus, let's redistribute this, 4 times x times 4 times h, so 4x plus 4h, plus 2, minus x squared, and I got to redistribute the negative sign here, because it's in front of the whole thing, so it's minus 4x minus 2, all over h. Let's multiply out this numerator, x times x is x squared, x times h is xh, h times x is hx, and then h times h is h squared. And we have a plus 4x plus 4h plus 2 minus x squared minus 4x minus 2 all over h. What's the limit as h approaches 0? This cancels this one out. These get combined into 2xh plus h squared plus 4x minus 4x get canceled out. Then we have a plus 4h, and then plus 2 minus 2 also get canceled out. So then we are left with all over h. You can see each term has an h factor, so we can factor it out as h approaches 0, h times 2x plus h plus 4. Think of factoring out as dividing by. So we divided this by h, divided this by h, and divided this by h. So we are left with 2x plus h plus 4. Still all over h. H divided by h becomes 1. So we're actually left with the limit as h approaches 0 of 2x plus h plus 4. If we let h approach 0, it goes away, and we're left with 2x plus 4 as our derivative. We can check that with the power rule. Okay, we know that f of x was equal to x squared plus 4x plus 2. So f prime of x is equal to the derivative of x squared, which is 2x, plus the derivative of 4x, which is 4, plus the derivative of 2, which is 0. So our derivative is indeed 2x plus 4. So that's confirmed with the definition of the derivative and with the power rule. We can also approximate it. So we know that the derivative is as h approaches 0 because we want our distance to be so small that there's no distance at all, right? It's approaching 0. So we can approximate using a really small value of h, let's say 0.1. That's pretty close. So we can look at the graph. Okay. So if we just graph Okay, so if we look at letting h equal 0.1, our f prime of x is approximately f of x plus 0.1 minus f of x all over 0.1. Well, we know our original function is x squared plus 4x plus 2. So we're actually looking at f prime of x is equal to f prime of x is equal to f of x is equal to x squared plus 2x plus 4. Okay, is actually equal to x plus 0.1 squared plus, it's 4x plus 2. Okay. Plus 4 times x plus 0.1 plus 2 minus x squared plus 4x plus 2 all over 0.1. So we can graph this function which is x plus 0.1 squared plus 4 times x plus 0.1 plus 2, and all that minus x squared plus 4x plus 2. And that whole thing is all divided by 0.1. Let's graph it. I messed up somewhere here. Oh, sorry, I forgot a minus right here. Minus. I don't know why it's not showing a subtract. There we go. Oh, whoops. Minus. There we go. And then that whole thing. Oh, there we go. I'm still missing something. I'm not sure what. There we go. Okay, so now we graph that function, and it looks like a line. If we look, it looks like the slope of the line is over 1 up 2. So the slope is 2. And we shifted up 1, 2, 3, 4 units. So actually, we found out using an approximation that our derivative is pretty close to 2x plus 4. Okay. So using our approximation, it looks like our derivative is again 2x plus 4. So you can use different methods to find your derivative. And depending on the problem, you may have to use the definition, use the power rule. Okay. You can also use the definition of the derivative to find the original function. So there was a problem we did in class where you were given this. Okay, we have some f of x, we don't know what it is. But we do know that derivative is written like this. The limit as h approaches 0 of 9 plus h squared minus 1 minus 80 all over h. So we wanted to know what was f of x and what x are we finding the derivative at. So it looks like I'm in the form of x squared minus 1, where our x value is 9. Because this right here should be f of x plus h. So our x looks like it's 9 because x plus h. So it looks like our original f of x plus h was x plus h squared minus 1, meaning our f of x is equal to x squared minus 1. And we can prove that with here, this minus 80. Okay, if we plug in f of 9, we get 9 squared minus 1, which is 81 minus 1, which is indeed 80. So it looks like our x value is 9, and our function was x squared minus 1. So we can use the definition given to us to then find the original function. Okay, so then our original function was x squared minus 1. We're evaluating f prime of x, which is 2x, and f prime of 9 is just 2 times 9, which is 18. Okay. Way to write the definition of the derivative is instead of x plus h, so instead of another x value h units away, we could write it like this. So here's my f of x, here's x, here's the y-axis. We have some x value at f of x. We can find another value a, okay? So here we are at f of a. We then, like in class, what we did was try to find how to write the derivative here then. So we want to make a secant line, and then we want a to get closer and closer to x. So we want it here, so that's a better secant line. And then if we have it here, that's an even better secant line, and so on and so forth. So we wanted x to approach a, and then we wanted to find the difference in y's over the differences in our x's. So this is something we figured out in class together. If you want to write it this way, so instead of it being h units away, we just have another x value a, and then we want x to get really, really close to a. So that's another way to write it. So I would say practice trying to find the derivative using multiple ways. So either first using definition, then using the power rule if it applies. Like obviously you can't use the power rule for something like sine of x. We don't know how to find that using the power rule. It's not a power function. But for things that are power functions, try to use the power rule. And also you can approximate by letting h be really close to 0 and then graphing. Okay, just like we did with that first example. So you can practice with 9 over x. F of x is equal to negative 3x squared minus 6x. F of x equals 5t to the negative 2. F of x equals 14x plus 2. And for this one, don't use the definition. Just use power rule because it would be kind of hard to use the definition for this one. Negative 3x to the 7th minus 6x and negative 2x to the 8th minus 6x to the 6th. Okay, so do some practice with these. Use the definition and power rule and see what you get. You should obviously get the same thing, right? One function as a derivative. And then with these ones, just use power rule, get some practice, okay? So there you go.